So I have I'm going to give a talk on this topic, that is automation in concrete construction. And as I want to tell one small incident that can you tell me what is that figure here? I can everyone has seen such dashboard of a car where we can get many information, right? We can get information of the speed of the car and the torque, I think, and how much petrol, how much fuel is available, how much distance you can go. So many informations are there, and we can have a, even if the cost of the car is about in the lower bound, it can be 6 to 8 lakhs, right? In a 6 to 8 lakhs rupees car, we get a lot of information about the vital information about the car. But in contrast, uh, I have put certain cost of certain projects, civil engineering projects. I got it from newspapers. There is a Ghosh Khurd Dam at Maharashtra. At 2012, its cost was about 8,000 crore rupees. There's another bridge, Dhola Sadhya Bridge at Assam. That is 876 crore. And I found one Kerala bridge. That is also I got it in the newspaper. In 2018, the cost was 113 crore. It is very close to Ernakulam. And one small building, not a small building, somewhat a moderate building in our campus cost 100 crores in our NIT Rourkela campus. So you see, there's few lakhs rupees of cost of this car and so much information. As a user of this car, you get to know how much petrol is left, how far you can go. But for the structures, we don't know how much life is left or what is the level of stress that the structure is subjected to now, and what is its capacity, whether it is close to failure or it's okay. That information are not available. So who is going to do that? What are the important information that we need to know, and where this information should be displayed? So people told, once I talked to a physics professor of IIT Kanpur, and he told me, you people build such a big structures, but there should be some display, and where all these some of the vital information should be there for the users. The user must know where they are entering. So now I want to tell you another important failure. You see, this is a very famous photograph of the accident of Skyline Plaza that happened in 1973. And you know, the reason for this failure was premature removal of soil. The formwork was removed prematurely. That means the construction engineers did not know that the structure is not ready for formwork removal. The concrete was not ready. That means it does not have the sufficient strength. It did not achieve the sufficient strength. And before that, the formwork was removed. And that accident happened in 1973. So you might be thinking that this is a story of 1973. Probably now it is not happening. I don't know, similar accidents are not reported, but in close to our campus, I have taken this photograph myself. This is in 2019 from a construction site at Rourkela. You can see what happened here due to the premature removal of formwork. So when the concrete is inside the formwork, and when you think that it is best to remove the formwork, what are the criteria? That means it should have sufficient strength. The concrete should have sufficient strength. Suppose you delay, that is also a problem. If you delay to remove the formwork, you cannot, it will delay your progress. The construction progress will be delayed. So suppose I have some information about the strength of the concrete before I remove this formwork, it will be nice, right? if we know what is the strength required before we can remove the formwork. So, and what is the exact existing strength, how much strength has been achieved. If such informations are available to us, then we can precisely remove the formwork. If we can save time, it will help us, it will reduce the project cost and the time. Or if we see the strengths are not sufficient, so we can assure safety by appropriate timing. Okay. Now, but the problem is paucity of available instrument for civil engineering structures, lack of technologies available for the automation of civil engineering construction. So we don't have instruments, right, uh, to place and get the information from civil engineering structures. There are no technologies also for automating this type of to avoid this type of problems. But you can be sure that the automation in construction industry is indispensable to significantly improve the productivity, quality, economy, safety, flexibility, accuracy, and whatever you think. Automation is coming in every other domain of engineering, but it is not that aggressively coming to civil engineering construction. So there is a scope of work for all of us, all the civil engineers in this particular area. So this is, as I said, is a big problem. A lot of things to be done. So we have in our group, we have started a small, I can tell, the first step forward in this direction. And last 2 years, some students are working, and I want to share what we have done, and that I feel will motivate all of you to give some of your interest, bring some of your interest in that particular area. So the problem that first we have started is monitoring of early age properties of concrete at real time. Early age properties of concrete. So during the construction time, how early age properties evolve, that we want to monitor at real time, means exactly at the same time we want to know the information. So early age properties of concrete. What are the early age properties? Important early age properties can be, workability, that we check in the beginning, workability, setting time of the concrete, then compressive strength and plastic shrinkage, and many other things. So we have thought the compressive strength is one of them, because that problem I told about the Skyline Plaza accident is about the removal of formwork that is directly related with the compressive strength. Then plastic shrinkage, many a times there are the construction managers are not directly visiting the site or the structure very minutely, precisely. So the construction managers are depending on the contractors are depending on the laborers to know the situation of the construction. So therefore appropriate measures to control the quality are not happening. But if we have a direct information system to the construction manager, structure to construction manager, without via anybody, so then it will help to control the long-term behavior of structure, quality, and safety, because now early age property is directly related to the long-term behavior of the structure. Many factors. Now, how do you get the compressive strength of the structure or the plastic shrinkage details, setting time details? How to get? You can. It is not a new thing that some of the everyone knows. In the published literature, you can find that the concrete temperature, atmospheric temperature, some of the measurable parameters, right? Like we can measure the concrete temperature, we can measure the atmospheric temperature, we can measure the relative humidity of the locality, wind velocity, that is progress that is happening in around the structure. Those measurable parameters can influence the development of early age properties of concrete. Even in the code you can find this. Now, if we can monitor such parameters, because there is a an direct or indirect relation with of this measurable parameter to those early age properties of our interest, right? This measurable parameters can be related analytically or empirically to those early age properties. Now, if we can monitor those measurable parameters, then they can be very useful in quality control and construction management, because we can, through those measurable parameters, we will assess the values of compressive strength and plastic shrinkage and whatever other parameters that we think of at real time. And it is not difficult, because the real advancement of sensors, microcontrollers, and IoT technology that gives you this opportunity to real-time monitoring of every concrete properties, right? And we can bring superior accuracy. We can reduce the cost of the structures by better construction management through this informations. Now let us consider, I will now concentrate on compressive strength of concrete. So how do you measure compressive strength when concrete construction is going on? We do check concrete compressive strength, and we check the quality of concrete through this parameter, the compressive strength of concrete. So what we do is we take specimens, either we cure it at the field itself or we cure it at the laboratory, and then we test it after a certain time, right? On 7th day or 28 days or 14 days, like that. Now, so whatever you are doing, a curing condition that you are doing for the specimen you may not be doing the same curing condition for the structure. So there is a variation of curing condition. So your field cured or lab cured specimens do not represent the curing condition. Definitely there are other conditions like your local environment of the specimen and local environment of the actual structure may be different. So it does not represent the in situ concrete. The specimens really do not represent the in situ concrete. So whatever strength you get for the specimen, they are not representative. Most often they are not representative to the actual structure. There are other problems. Let us assume that they are giving you actual info representing the structure, but you are getting a delayed result. You are knowing the problem at 28th days or 7th day or 14th day, when you are not in a position to make a change in your structure, right? So therefore this is not useful in that sense, right? When you know the problem, by that time maybe the structure has progressed certain amount, and you cannot again dismantle that part and correct the problem, right? So you have to do some other thing. So that is another one more problem. So to support this, there is an instrument called concrete maturity meter. What is that concrete maturity meter? Concrete maturity is a very is an old parameter. That maturity is a function, temperature time function, TTF, temperature time function. So it is in different codes and standards, this temperature time function is directly correlated with the compressive strength. So this is like 1 day, 3 day, 7 day, and 14 day. From this function, temperature time function, we can find out what is the compressive strength at different time, right? So this maturity is a relationship the maturity is a temperature time function, and there is a relationship between this maturity and the concrete strength of a given mixture, and this relationship used by this concrete maturity meter, and it can tell you the uh, the progress of strength, or the how the strengths are evolving at the early ages. So what is this maturity method? Maturity method is a concept that existed since 1950. A non-destructive method. It is a non-destructive method to estimate the strength development. One second. Yeah. A non-destructive method to estimate the strength development of in-place concrete, specifically at the early age. Early ages means less than 14 days age. This method gives you the strength development in place concrete, means in situ concrete. It uses the temperature history, temperature time factor, that means how temperature is progressing, concrete temperature, right? Temperature history of the concrete to estimate the strength development. So temperature history will give you the strength history. The compressive strength of hardened concrete is a function of the rate of hydration of cement and is proportional to the internal temperature time history of the concrete. This is the primary assumption. What is the primary assumption? That the hydration of cement is proportional to the internal temperature. You know, when hydration happens, the heat of hydration will increase the temperature of the concrete. So if you see the temperature of concrete is high, that means rate of hydration also high. Therefore, the temperature of the concrete is related to the rate of hydration. This is the assumption. And if rate of hydration is more, the strength also will be more. So this is the underlying assumption in this maturity method. And it is this method is there in the different standards and codes, right? Design codes and standards. Now, this strength maturity relation is like that. These two codes I'm referring here. One is the ASTM code, and other one is a CBFIP model code. So there's a mistake here. It's a model code, and this is, you can think, an European standard, and this is an American standard. So in this standard, FC is the compressive strength at a particular time, is a function of log m. M is the maturity, and A or B are the constant that we have to calibrate, right? So what is the M that I'm going to discuss little later. Next slide. And this is as per the American standard. And European standard, again, FC has a particular time. This maturity also changes with time, right? This FC changes with time, maturity also M also changes with time. Here FCM is a constant like A and B, and R is another constant. Here two constant A and B, here two constant FCM and E is exponential of R times 1 minus square root of 28 by TT. This TT is temperature adjusted age. This is also kind of maturity. So this M and TT are kind of maturity, and there is a relation between strength and this maturity, where FCM and R, A and B, they are the constants that we have to find out while calibration, when we do calibration. Now what is this M and TT that is here? Okay, so this R value is already, this R value is introduced by this European code, and this code gives you the value of R directly. For compressive strength, mean compressive strength, if it is less than 60 megapascal, then there are various values of R depending on the strength class of the cement, right? And if the mean compressive strength of the concrete is greater than 60 megapascal for all classes of cement, it should be 0.2. So this is for the value of R, and this slide shows you the maturity or temperature time factor. So as per the American standard, the first equation, you know, M comes from the ASTM code. There it is, M is equal to TCI minus T naught into delta T. So TCI is a particular time and sorry, TCI is the temperature of the concrete temperature at particular instant, and this T naught is a datum temperature in degree centigrade, and delta T I is the time step. I'm going to show you a plot for better understanding. And similarly here, this delta Ti is the time step, and e power, this TCI and TCI is same. So at particular TCI we know what is the M, and that particular TCI we know what is the TT. And this figure shows this maturity as per the American standard. So you see, so this is the concrete temperature. At any time concrete temperature is here, and it has been divided into several time steps, and at that time, and there is a datum temperature that we will discuss what is datum temperature. So TCI minus Ti, and the summation of that into Ti. So for if we find out the maturity here at this time, at this edge maturity, you should have a integration or the summation of this area, right? This shows that area under this curve. So at a particular time, the area up to that portion will give you the maturity. And this datum temperature is defined as the temperature above which the hydration process and strength development of concrete are most likely to begin. So datum temperature is defined as the temperature above which the hydration process and strength development of concrete are most likely to begin. So therefore, if I keep measuring the temperature of the concrete, and if I know the datum temperature, I will know the maturity, right? I will know the maturity. As the time progresses, our maturity will be increasing. So if I know the maturity, I will put this maturity in this equation, and I will know the strength of the concrete at that particular time. Again, as the time goes, your maturity will increase, and my strength also will increase. So how the strength is gaining over the time in the early age, we can predict. Similarly, we can do for this using this method also. So we are not developing these methods; these are already existing. 1998. So for the more than 20 years, these methods are available. And based on this method, this maturity method, a maturity meter works. And now see how to find out this datum temperature. This datum temperature comes only for American standard, and code gives you some procedure how to calculate this datum temperature. Otherwise, you can take conservatively some values. The code says some values, but it is not very difficult to develop this value of datum temperature. As per this code, for a given mix of concrete, strength edge relation of mortar specimen. So for a mortar specimen, only the mortar specimen, whatever the cement is to aggregate, similar cement is to sand, mortar we have to prepare. And for this mortar, for the given mix, so one mix represented by cement is to aggregate, and the cement to water ratio, water to cement ratio. So that keeping everything intact, we can develop the mortar specimen of a particular mix. And you see the first figure here. There are 4 figures. The first one shows the age versus compressive strength. So at 3 different temperatures as per the code. So that is 10 degrees centigrade, 20 degrees centigrade, and 30 degrees centigrade. At 3 different temperatures, experimentally we can find out. We can develop this mortar specimen, keep this mortar specimen at different temperature berth, and then we can test the specimen and find out the compressive strength at different time, different ages, up to 32 days, and we develop this plot. This is strength edge relation, right? Now here we can derive this plot, that is 1 by inverse, 1 by compressive strength in the y-axis and 1 by age in the x-axis. And here this ST. So this will be 1 by ST in megapascal, and this is in days. So now whatever plot we can get a best fit straight line. We can make a best fit straight line, and this best fit straight lines are going to cut the ordinate at different points here, and this will be, so this ordinates again, if we take inverse of them, we get some values of, in terms of megapascal, some strength values, and these strength values are denoted as S infinite. So very simple. Once you can, in laboratory you can develop that and find out this S infinite for 3. So 3 S infinite I will get, and so now Ct is an intermediate constant which is equal to St divided by S infinite minus St. So using this formulation I get a plot of C versus H. So just converting same plot in a different form, and when I get them again, I make best fitted straight line and take the slope of these 3 straight lines. So these slopes are known as K, rate constant. So now I plot the rate constant here, rate constant versus, so rate constant for 10 degrees different, rate constant for 20 degrees different, and 30 degrees different. So I plotted here and make a best fitted line, and it cut the abscissa at a point, and this is marked here in the red circle, and this is taken as the datum temperature. So this procedure is outlined in this code. So we can find out the datum temperature. So once we know the datum temperature, what is stopping us? So if we know the datum temperature, I will record the temperature with time, temperature time history, and I will deduct the datum temperature, and whatever is the age, at that age I take this area, I get the maturity, and from this maturity I use this formula to get the FC. That is the thing this our maturity meter is doing. Therefore I can find out the strength. But what is the problem with this maturity meter? There are certain drawbacks. I will not say drawbacks. Certain problems with this maturity meter. The manual recording of compressive strength. What they do is they put a sensor inside the concrete while casting, and then maybe some Bluetooth mechanism. They send temperature data to this instrument, where you have a SD card here, and you take you have to go with this instrument to the site, and then take the temperature data at a particular time, come back to your computer, process this data, and you find that these equations are there in your computer. So you need a software to process this data, which your computer will tell what is the strength. So it is not a continuous process. You will get intermittently the compressive strength data. There also will be a lag of time, right? When you go and collect the temperature data and you process it, you will get a data that is not exactly at real time. Somewhat there is a mismatch of time. So manual recording of compressive strength of concrete at the site by measuring the internal temperature. As this instrument is operated manually, frequent recording of internal temperature is cumbersome for real-time prediction of compressive strength. A software program is generally required by the conventional maturity meter to extract and analyze the data in a computer. That means again you have to trust another guy. The construction manager will send someone to get the data, and he has to depend on his performance, right? When he will process the data and get him the values, but by the time it is not the real time data. So our objective of this today's presentation, my objective is to show you how we have automated this procedure. How to overcome this shortcoming? To automate this procedure, an IoT enabled setup is proposed for real-time monitoring of early age compressive strength of concrete using the principle of maturity method. So we are not going to tell you, I'm not going to tell you a different method, the same method, but I want to show you certain avenue, some procedure which will truly make this system automatic. And these two codes are we are also following the same two codes. And now I said here IoT enabled setup, right? For us civil engineers, we don't know what is IoT. What is IoT? I also did not know 2 years back. Recently, I came to know about that. IoT is Internet of Things, a network of interconnected devices that can communicate the data gathered from a monitored field through a wireless link. This is what the definition I got. And there is no human interaction required. It is only machine to machine communication. So you see there are some devices, the same sensors and actuators, whatever devices are there, they send the data to a gateway. From gateway, the data goes to cloud platform. From cloud platform, you can get the data in any application that you want. So I hope you are clear about what is IoT. So this network, which is interconnected, network of interconnected devices that communicate the data gathered from a monitored field through a wireless link, and it does not require any human interaction. So you can directly from device to your application, you get the data. So a little more simplification of the same thing. So I can measure the data through sensors. For example, temperature. The problem now we are discussing here, temperature is the only data we need, concrete temperature. So temperature, humidity, pressure, motion, anything. So all the sensors, we can get the data from sensors to the gateway, IoT gateway or framework, and through wireless communication, the data are stored in the cloud server, and from cloud server, anybody can access the data in a even in your mobile phone, mobile app. So the construction manager can, if we can use this architecture, we can get the data in the mobile phone of the manager, construction manager, from the structure itself. So the condition of the structure will be in the mobile of the construction manager directly. So the broad methodology, so it is as simple as that. So broad methodology is, first we calibrate the for a given mix of concrete, we calibrate this maturity method. What is that meaning? That means we find out the datum temperature and also the constants that we have to find out for calibration. So once we know the constants and the datum temperature, we know the strength maturity relationship. So that we do at the laboratory, strength maturity relationship. Now once we know that, so this strength maturity relationship is completely known to us. Now we assemble this IoT enabled system. We assemble the system and then we deploy it at the field. So what this IoT enabled system is, it is like an interconnected devices. Is a framework of interconnected devices where we have this equation of strength versus maturity relation is already inbuilt, and the sensors here in this IoT enabled system, a field will find out the concrete temperature, and the concrete temperature will help to calculate the corresponding maturity and therefore corresponding strength, and the strength data is going to be available in the any remote location devices like mobile phone. So in our problem, we need only a concrete temperature. So in a structure, we put a sensor, and the sensor is connected with a is a wireless connection, although is a Wi-Fi microcontroller. We need a Wi-Fi microcontroller because this Wi-Fi is required for sending this data to cloud platform. And what data it collects? It collects temperature versus age. So as the time progresses, how the concrete temperature varies, that record is called temperature history, temperature time history. So once we have the temperature time history, from there we can find out the maturity. So maturity will keep increasing as the age progresses, and from this maturity data we find out the strength data, because already we have maturity strength relation. So strength versus age data, and this data, it goes to the cloud platform, from cloud platform to mobile or laptop, everywhere you can get. So it is a smart and cheaper system than conventional maturity meter for predicting early age compressive strength. This is as simple as that. Now I will tell you a little detail about that. We have chosen a temperature sensor this looks at temperature sensor, and you see the size of that in comparison with, so the sensor is actually very small, and there is some weird connection to connect it with microcontroller. And digital waterproof, this sensor is digital waterproof, it has to be waterproof, and one wire interface. And also this sensor is it can resist the alkaline type environment of concrete. A pull-up register is connected between the power and signal line of the sensor to prevent it from damage due to excessive heat. So sometimes the sensor has a problem with excessive. So these are the detailed specification of the sensor. So it has a temperature range. It can record temperature from -55 degrees centigrade to 125 degrees centigrade with accuracy of 0.5%. So it's almost like less than a degree, 1 degree centigrade it can record. Humidity range is not, we don't need a humidity, and a sampling interval. So at every 0.75 second it can record the temperature. The body size is 4 millimeter diameter, and it requires a voltage of 3 volt to 5.5 volt. The degradation in the signal over long distance is well within the limits. So this is a already tested sensors. People have used it in concrete. Now to check the accuracy or performance of this system, this sensor, we have brought another system, another sensor, which is STH10, and this is our DS18B20. These two sensors are recording temperature for a particular concrete. You can see they are almost very close. So the temperature data measured by these two sensors are in agreement with each other with a difference within the 1%. The difference is less than 1%. So we have when the two sensors are giving same data, we can accept that their data are correct. Now we need a microcontroller. Sensor will record the temperature data and send it to microcontroller. But microcontroller will process the data. That means microcontroller has all this program. That means it will calculate the maturity, it will calculate the strength. The program here will be calculated. So it is a small in size. Size you can see in comparison with the 10 rupees coin. It is low cost, and it is a 2.4 gigahertz Wi-Fi microcontroller and can make a simple TCP/IP connection supporting 802.11 network. So these are some electronics information. So total setup is like that. We have a board where this microcontroller is attached here, and this sensor is also attached with the board, and this sensor will be actually inserted in the concrete, and the concrete temperature will measure and send the data to microcontroller. So DS18B20 sensor is connected to ESP8266 Wi-Fi microcontroller, which will connect to the internet and post the data in the cloud. So you need to have a Wi-Fi router also. So the availability of internet is required so that this microcontroller can send the data to cloud. And thingspeak.com, we need a storage platform in the internet, and there's a presently we are using a thingspeak.com, a cloud platform, to receive the data from wireless sensor nodes through the internet and to supply the information wherever required for further processing and display. And you see the red line shows a typical in ThinkSpeak also we can get this data, this temperature versus time data. You can see here thingspeak.com, and we are getting the time history of the temperature, concrete temperature. The prediction of the, so what is the total, I want to summarize the total procedure. The prediction of the early age strength requires the strength maturity relationship of the given concrete mix. The relationship for the given concrete mix must be calibrated with actual strength data for accuracy. DS18B2020 sensor records the internal temperature of the concrete in real time and sends the data to ESP8266 Wi-Fi microcontroller. Microcontroller calculates the early age compressive strength based on the developed strength versus maturity relationship for corresponding concrete mix. So, is that clear to all of you? Now, how it calculate? It requires a program, right? So, Arduino integrated development environment is used to program this microcontroller using a C programming language. So, this is the program that calculates the strength or maturity from the temperature time history. A new channel was created in thingspeak.com containing the following fields. So, in thingspeak.com, the microcontroller sent data of temperature at real time, maturity index at real time, and corresponding early age compressive strength also at real time, right? The address of ThinkSpeak channel and the Wi-Fi login credentials should be provided in the C program, because the C program is going to send the data. So the address of the channel, that cloud platform channel, and the Wi-Fi login credentials should be provided in the C program fed into this microcontroller. The microcontroller shows the data in organic. Again, we can put a one display, right? We have put a organic LED display, OLED display in the site itself, and at the same time it can send the data to the cloud platform at real time. So one can see when you are present at the structure, you can see the real progress of the data at real time, and from a remote location you can access it through the cloud platform. So the entire setup needs to be protected from voltage fluctuation and power loss. So you have to have a UPS. So this requires power. So one uninterrupted power supply is utilized for this purpose. So first part is to calibrate the compressive strength versus maturity index, strength maturity relation. That you have to take some specimens and take compressive strength versus age. From there, maturity index versus age will be calculated, and as per this code, the ASTM code or European standard CBFIP model code, and from there we can find out this compressive strength versus maturity index. And once it is done, now this system is going to be deployed at the site for prediction, and at the site it will calculate the temperature, and from there it will develop the maturity, and it will develop the compressive strength at real time. Now for this whole thing, what we have used certain material. So it shows the material property of the cement that we have used and the material property of the aggregates that we have used, and you can see here they're all standard tests like setting time, specific gravity of cement, and Portland slag cement we have used, fine aggregate specific gravity, and specific gravity of coarse aggregate, and this is the gradation of the aggregate, coarse aggregate and fine aggregate, and they are all within the limit of the code. Now the mixed proportions, 5 concrete mixes are selected for this experiment program, for this program. So for different, you see here, by changing this water cement ratio, different strength values of this mix. So 5 different mixes are selected from published literature, and these 5 mixes are used for this case study. So corresponding to the 5 concrete mix, 5 mortar mixes are prepared, right? 5 mortar mixes representative of each of the concrete mix, as I was discussed, that cement to aggregate ratio and the water to cement, this ratio are kept constant, and the 5 mortar mixes, representative mortar mixes, are prepared, and they are cured at constant temperature, 3 constant temperatures, 10 degree, 20 degree, and 30 degree. And compressive strength test, break test, right? The specimens are broken in a compression testing machine at 12 hours, 1 day, 2 day, 4 day, 8 days, 16 day, and 32 days. So that is the first thing done. And you see the at 10 degree, you have 5 mix. What is the at 10 degree temperature? When it is cured at 10 degree temperature, how the compressive strength versus age data progressed, and this is at 20 degrees, same figure at 20 degrees centigrade and at 30 degrees centigrade. So once you have this data, we find out the procedure of datum temperature calculation. You must remember, and these are actually average of 3 specimens. Please note that. So we found out the datum temperature for each of the 5 mixes. So datum temperature at degree centigrade T naught is the datum temperature. So that was one precondition for our procedure, right, for this maturity method. Now the next thing is development of strength maturity relation. 18 cylindrical concrete specimen of each mix. Once we know the datum temperature, now we are preparing cylindrical specimens. We are doing 18 cylindrical specimens of each mix. A total of 90 specimens for 5 mixes are cast as per this code. Temperature sensors are inserted in the fresh concrete of the 3 cylinders for each mix during the casting to record the internal temperature of concrete at every 60 seconds. At all the 18 cylinders are placed in the curing in a water bath. 3 concrete specimens from each concrete mix are tested in compression testing machine. After, so 3 specimens are tested in the compression testing machine, break test, at different time to know the actual compressive strength. And other machines, other specimens are giving you the maturity values, and we are assessing the temperature through the maturity method. The Wi-Fi microcontroller receives the data from these specimens and automatically computes the maturity indices of each mix. So you see here, this many specimens are there. 3 of them are instrumented and others are kept for break test. So these 3 are not broken. They are kept to send the temperature data continuously up to 32 days. And from this temperature data, the maturity index is calculated, and these specimens are meant for the break test. And you can see here how in the red circle you can see a white color thing, and here also that shows that the location of the sensor inside the specimens. So it is something like that. In a curing tank, we put the 3 specimens for each mix, right? 3 specimens are giving you the value of temperature. So we can take an average temperature value, that average of these three data, and from this temperature value we can find out the maturity, right? The temperature time function maturity. How we get this data, and this data again we use the same methods. There is a Wi-Fi network, and with the help of this Wi-Fi network from this microcontroller, so these are the temperature sensor, this is the microcontroller. So microcontroller is sending data to thingspeak.com, and from thingspeak.com we can find it, take it in our laptop or any mobile phone. So this laptop, we are getting the maturity values, and we are breaking the corresponding specimens at different age to get the actual strength. Then we can this is a photograph of a laboratory. You can see here all this are connected with this this board that we have shown you earlier. So this is, if you take a closer view, this shows the details of closer view. So the 5 mix, and there is a UPS and a Wi-Fi router is required. There's a Wi-Fi wireless Wi-Fi network is here, so it can give you data. And in the thingspeak.com you can see how maturity is progressing over the time, this red line. Okay, so now we have plotted maturity index versus age as per this code. As per this code, we find out the value of log m, right? So maturities are known to us, and if you use that, we can find out the value of A and B, right, by this age maturity index curve. And this is for CBFIP, that is temperature at TT versus H, and we find out that FCM because R is already known to us for a particular mix. So code gives you the value of R. So what are the constants A, B, and FCM? So A, B, and FCMs are noted here in this table for 5 different mix. So once we know these values, then we don't have to just calculate the maturity index. Now we can calculate the. So far in this experiment, we are calculating only maturity, right? Because we did not know the relation between maturity versus strength. But now, after this exercise, we know the relation between strength and maturity. So next time, we don't have to calculate only maturity, we can calculate strength directly. So now to validate this, what we have done is a set of 15 concrete specimens is further cast. So next time, another 15 specimens are further cast for each of the 5 selected concrete mix. So 5 into 75 specimens we have mixed, 15 for each of the mixes. Now proposed IoT-based system was implemented for 3 out of the 15 specimens, and remaining 12 specimens were tested for compressive strength at ages 1, 3, 7, and 14 days of curing. The experimentally obtained strength, the mean of 3 specimens, are compared with those predicted. So now I will show you. So this is what we got, the values. That is the age versus compressive strength. You can see this actual is by one square mark, and circle is the predicted as per the European code, and triangle as per the, these are the legend as per the American standard. And you see they are almost within the tolerable range, right? The errors are within the accepted range. And this is at mix 2. So 1 and 2 mixes are presented here. 5 mixes are almost similar type of results we got. And for one mix, I have shown you a detail the type of error that we got, and for other mix we got similar type of results. And here we can see the error is little high for ASTM in the early ages, very early ages, but as close to the 14 days, the error reduces, right? And CBFIP gives you a different results. Here the errors are comparatively low, but here errors are higher than ASTM. So the error presented here is, so you have to note here that this error is not the error of our system. There are some error also which is associated with the method of maturity method that is outlined in the code. So code equation also has some problem, and some problem may be there in our implementation of that. So the error presented here is combination of inherent error of the maturity method and accuracy associated with the proposed system. So is a combination of these two. But still we will see that we can have a very nice if you compare the actual value and the predicted value, you get a very close to the actual value, right? The predicted compressive strength is very close to the actual values. So the whole thing now in the initiation stage, create a new channel containing field that is temperature, maturity index, and RDH compressive strength in thingspeak.com. Assemble the IoT based system, develop strength maturity function in the laboratory, power the IoT based system, and insert the IoT based temperature sensor in the fresh concrete, power Wi-Fi router, and connect it to the IoT based system. And monitoring stage, display the real-time values on thingspeak.com. So it is like that. So same maturity meter we have developed as little different but very effective one. You must be thinking that it is very expensive. So we have made a cost comparison. So IoT based system is developed for early age compressive strength is cheaper than the conventional maturity meter. And it is, you see, to purchase a maturity meter, it cost about in US dollar 1,000 to 1,500 US dollar. But the whole test setup for us, it took only about less than $50 US dollar. And you can have cloud connectivity to the proposed IoT based system, and Wi-Fi connectivity, through Wi-Fi connectivity we can have. And but this maturity meter do not have such options, and it requires human intervention, whereas for this system does not require any human intervention. And you get monitoring at real time. You can also get monitoring at real time in conventional maturity meter as they claim, but actually there will be some delay delay, right? So you don't need a software or data logger for this system. It can gives you directly the data, but for maturity meter you need a software to process the data, and you need a data logger to receive the data. Now I will just conclude by telling you our initial problem of vertical formwork stripping. So we have applied this procedure for a vertical formwork stripping, and you see, when you have to remove the formwork, I told you about the Skyline Plaza in accident, that people removed the formwork prematurely. So we have checked the codes. You see what is the different time. Code says there are different codes: CBFIP, American Concrete Standard, British Standard. This is German, Dean's, Indian Standard, Australian Standard, and it says that you can remove the vertical formwork after 9 hours of casting, and some other code says 24 hour of casting. So it varies from 9 hours to 24 hours of casting. And definitely you see the ages when these codes are formulated, and it is not clearly mentioned, but most often these numbers are based on a particular type of concrete, right? Maybe Portland cement concrete. But recent development in concrete technology, we are using so many things. Sometimes fly ash, silica fume, then many other things at mixtures we are putting. So we cannot directly use these values, right? If we get exact strength of the concrete at a real time, and we know at what strength we can remove it, then it will be better. Also, some of the codes and literature. These are some of the literatures and codes. They say the minimum strength, compressive strength required for removal of the vertical formwork. There are two types of formwork. One is vertical formwork, which is non-load bearing formwork, and horizontal formworks mostly load bearing formwork. So we are now discussing about non-load bearing formwork. So if the structure is sufficient, if a column concrete can stay alone without the support of the vertical formwork, then we can remove the vertical formwork. And this is the concrete strength that codes and literature suggest that this is the strength required for removal of vertical formwork. Here also you can see it is varying from 2 megapascal to 10 megapascal by different literature. So much variation. So which one to trust? Now we tried with our instrument, and based on, so here one interesting thing we did, you can see here that everything is happening from between 9 to 24 hours. So the strength maturity relation, it considers about 0 to 14 days, right? This early age property is up to 14 days, but 14 days is too long. So to have more accuracy, we have developed the strength maturity relation in only for 0 to 72 hours. We have considered data for 70, not this 32 days data. We used only the 72 hours data for a finer maturity strength maturity relation. 72 hours, because we felt that it will be within that range, 0 to 72 hours. So this maturity relation is not the same as the one last time I have shown you. There is a difference because it is developed only for the data from 0 to 72 hours. Now you can see this is some of the columns we have casted in PVC formwork. This is in our laboratory, and while casting, you see we have you can see here small that equipment instrument that we have put here, that IoT based system, and a little closer look is shows how it is, and this shows that this instrument in a casing, right? This is our this microcontroller, and here there is one sensor, one additional sensor we have kept here that is not necessary for some other purpose, but here it is the temperature sensor, DS18B20 sensor, and we find the output of the system. So we can find out concrete temperature. So how concrete temperature varies in the thingspeak.com, and how concrete strength increases, some of the data at a particular stage. And if we see, this is the data that we have received from this system, and this says predicted compressive strength versus age. And we have seen almost like 11 and a half hour or a little more than 11 and a half hour, there is no progress of strength. At this point, the strength initiation happened, right? Strength started forming, developing. So then it goes like that, strength goes like that. So compressive strength was almost zero, is zero in fact, right? Zero up to 12 hour, I can say. And then it started growing. So for this mix that we have used, this is for port and slag cement, 9 hour we cannot remove, right? Because there is no strength for at 9 hours. So 9 to 12 hour is not actually the, if you see here, many people have suggested 9 to 12 hours. Many codes have suggested, so that is not the case, at least for this mix that we have used. And you see the stripping of formwork. So we have several columns we have casted, and one column we 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 have monitored the compressive strength in one column, and other columns we have removed at particular time. So this is the column we have removed at 13 hours. This is the column we have removed. We have stripped the formwork at 15 hours, and here we have stripped at 17 hours. And seeing the visually how it how the surface is, you can get a sense that 13 hours is a little earlier to remove the form. Maybe 15 hours is appropriate, and 17 hours is definitely, if it is 15 hours is okay, it is also, it looks okay. So in a qualitative sense, I can tell 13 hours is early, 15 hours may be right. Yeah, okay. And then you can see the data that we have received. So actual strength. So we have also kept some specimens, cube specimens, or cylindrical specimens corresponding to each of this column construction, and these actual strengths are from their Brecht test values, and predicted strength means it is predicted by this IoT based instrument, and you see the error that we get, and from there you see this 1 megapascal or 1.25 megapascal, this is the strength which is required for getting a surface like that, right? So maybe we can have a conclusion that's about 15 hours or 1 megapascal is minimum required for that. But anyway, these values of 15 hours and 1 megapascal is very specific to this mix that we have used. For different mix, we should do another test and check for different. So, but once we know that 15 hours is required for this mix, and if we use the same mix in the site, we can remove the formwork at 15 hours, or else we can put this IoT based system in place and wait for the strength to achieve this 1 megapascal, compressive strength to achieve 1 megapascal, and then we can remove the formwork. Now another important thought is like that Santhanam and Getu in one paper, they have reported that non-load bearing formwork can be removed from the concrete members once the concrete reaches the final setting. So when the concrete reaches final setting, then we can remove. So we wanted to see when we can get this final setting. So for that, there is a penetrometer test by STM, for which we can find out the setting of concrete mix, not the mortar mix, right? And there, when your penetration resistance is reaching 27.6 megapascal, we can call that is a final setting. So it is like penetrating a rod and finding out the resistance. So initially the resistance will be low, and after certain time, when the resistance crosses this 27.6 megapascal, we consider. So this plot is a penetration resistance versus age plot. So you can see that 27.6 megapascal is coming at it's almost like at 15 hours. So this 15 hours is because it is also approximate, right? So this is one of the examples where we have tried to use this method. And yeah, hello, is there a problem, Babu sir?
No, sir, now it's okay, sir. Now we can see you actually, not the slide.
Okay, so I will again share the screen, right?
Yeah.
Is that fine?
Yeah, you continue.
Yeah, so similarly, we can do several other things like stripping of horizontal formwork, curing condition, monitoring curing condition, and different other laboratory tests without the help of any expensive laboratory equipment. I found that third one is very useful, because to do any test in concrete, you need somewhat expensive laboratory equipment. But using those methodology, we test everything, almost everything of concrete by spending a few thousand rupees in our laboratory. Maybe it is not direct, somewhat indirect measure, but still I feel it is good enough. And if you are interested, I want to show a couple of slides on this is the plastic shrinkage crack. When you cast a concrete, bleed water comes out of to the surface of the concrete, and if you have a higher evaporation rate due to wind and the humidity and the temperature, the atmospheric temperature, then you find crack and you require curing water at that point of time. But many a times in real construction site, people are not giving attention on curing. So we thought to check this evaporation rate and bleeding rate through this sensor and get the information to the project manager, so that he can intervene and take necessary measure for better quality. So some of the formulations are already available to find out the evaporation rate, and it depends on temperature of concrete, relative humidity R, temperature of the atmosphere, and the wind velocity. Similarly, this is on as per the code ACI. I have not mentioned, this is ACI 305 R, and there are some other equations where these are the three parameters. So if we can measure the concrete temperature, atmospheric temperature, relative humidity, and wind velocity, and we can easily measure the this rate of evaporation. And the code says if rate of evaporation is less than 0.5, there is no probability of plastic shrinkage to occur. If the evaporation rate is 0.5 to 1, there is a medium probability. If it is greater than 1 kg per meter square per hour, this is the unit for evaporation rate, and then there is a high probability. So we can measure this evaporation rate through this indirect measurable parameters, and then we can check whether it is growing if it is more than 1 kg per meter square per hour or more than 0.5 kg per meter square per hour, and we can take an corrective action, right? And for that similar type of, I just wanted to skip some slides. Here, this is the sensor to measure wind velocity. This is the same sensor, DS18B20, to measure the concrete temperature, and there's another sensor which measures both relative humidity and the atmospheric temperature. So we have put together, and this is the microcontroller, same our ESP microcontroller. So we have put it here and made a system for that. But in the laboratory, varying temperature, atmospheric temperature, wind velocity, and relative humidity is a difficult job. So my students have tried a temporary setup where we can vary temperature and wind velocity and relative humidity, everything, and check. And we found something like that. The plastic shrinkage crack to form by forcing different parameters. And these are some of the data that we have got in our cloud platform. And we found that if this type of information we can get, right, that rate of evaporation is exceeding particular value, 0.5 or 0.4 here, 0.5, and somebody has to cure the structure to stop this plastic shrinkage crack, right? If this cracks happens, then the long-term behavior of the structure will be compromised. So with that, I want to make a concluding remark that IoT-based system is developed for real-time monitoring of earliest properties of concrete, which is very cost-effective and which will help the control of the quality, and also it can bring economy in our project, and it will help the project management effectively. So also whatever I have presented here, I want to acknowledge that the entire work, all the credit goes to my students. I have understood the problem from them, and they have executed the work, and I'm just presenting on their behalf. Thank you very much. Now I can take up a couple of questions if you have.
The participants are requested to ask some questions.
Pradeep sir,
Yes,
myself Sandeep. I am from Muthoot itself.
yes.
Sir, I just joined late anyway. Sir,
Yeah.
can you just give me some more details regarding the importance of that datum temperature?
See, datum temperature is just a moment. Datum temperature is required to calculate. See, if you are using this ASTM method.
Okay.
1 second. Yeah. So in ASTM method and this Europe CBFIP, both places you need this M and TT, right? The M, in the calculation of M, it requires a value T naught. Unless you have a datum temperature, you cannot find out M. And if you cannot find out M, you cannot find out the FC. So this M is an integral part of this formulation.
So my doubt was actually the datum temperature means the temperature in the initial stage when we cast the cylinder.
No, temperature is something like that. I'll tell you. You see, here it is. Datum temperature is defined. This is the line of the code that I have kept here.
Okay.
Datum temperature is defined as the temperature above which the hydration process and strength development of concrete are most likely to begin.
Okay. Okay.
So this is the concrete temperature. That means that temperature, when hydration is enough to initiate the strength, you get a temperature. So that temperature is the datum temperature. So maturity will be calculated beyond that temperature.
Okay, sir.
Pradeep, I have a doubt.
Yeah, sir, please.
Whether this method is applicable for all types of structures, sir?
It is applicable for all type of concrete structures, sir.
Concrete structures,
yes.
Like a slab, beams, or
yeah, this is for concrete. See, it will give you the compressive strength development in the early ages. Now, why you need that compressive strength, that can change, right? Like for a vertical column, we have done this test to check when we can remove the formwork, and we have come to a conclusion that 1 megapascal strength is enough when you can remove the formwork. But for a slab or beam, this 1 megapascal may be higher, right? It must be higher because it has to take its own weight. Now, for a vertical formwork, the weight is transferred. There is a direct load path, right? But for beams and slabs, the load path is different. Otherwise, the method is same.
Okay. Then while taking the temperature for the calculation of maturity, if we are taking the temperature of the concrete outside temperature, what is going to be happened?
No, no. This is because this is the hydration. This temperature is due to the hydration heat. So
Yeah,
outside
you
you
want
won't be able to
the
get that.
temperature due to hydration.
So you have to get the inside concrete temperature.
Oh, okay. Then whether it will affect that is because by the maturity is the product of time and temperature.
Yeah.
While increasing the temperature, with the strength also will be increased in a short time. Now, whether that strength will be affected in any way in the ultimate strength, whether that initial increase in temperature beyond a certain limit will affect the ultimate strength of concrete.
See the definitely, sir. The early age properties affects the long term behavior of the structure. That means if your initial there are some of the, like if you add some admixtures in a concrete, it will slow the process of the initial strength gain, right?
Okay.
But in the ultimately that also you can check, right? Some of the admixtures when you add, you must have this experience that if you add admixture, it will delay the setting process. That means it will delay the strength gain in the early ages, but in the later stage it gains the full strength. So that can happen.
Okay. Then in the cost comparison,
yeah,
you're saying that the IoT based one is more cheap compared to the maturity
yeah, it is very cheap because they are in 100 rupees, 200 rupees.
Yeah.
This
Then in result wise, which is better?
Now, sir, both the instruments, see here the maturity meter and IoT based setup, they are using the same formulation.
Okay, okay.
Exactly same formulation. So this also using compute this temperature from a sensor. IoT based setup also using a temperature. Here everything is like a user defined. You can buy a little expensive sensor to get a little better values.
Okay.
Otherwise, we have tested in laboratory that it gives very almost close to, the errors are not that big. Although we have not tested the error associated with this maturity meter, but if you can check in the computer, you can buy a maturity meter, it will give you a cost something like that. But the same thing you can build in $50 in US dollar, but in Indian rupees it will be another into 80, right? About 4,000 rupees. Yeah.
Okay. Okay. Thank you. Please, any other
Yeah.
questions?
Pradip sir, relating to that,
Yeah.
I have heard that you have used ESP, right, for
Yes,
microcontroller.
yes, yes.
So I have heard like this Arduino as well as ESP is not useful for a long-term study and all.
I
They are
will
just
tell you, there are certain disadvantages I forgot to mention. This disadvantages is now, you know, when you are going to actually install it in the site. Let me show you this one of our laboratory setup. Yeah. So you have a wireless one router, Wi-Fi router. It
yes.
does not have too much of length, right? It cannot work for a very long distance. And so you need an UPS. Now
Okay.
for all these things at a project site, getting a Wi-Fi thing in a real project, it will be very long site, right? So it is difficult. And what you said also somewhat true. So in a small duration laboratory scale experiment, it is doing good work, but in a implementation of a real field, so we are now trying, there is a, if you are aware, some technology called LoRa, which has a long range connectivity.
Okay. Okay.
That is like I heard it can take 2 kilometer by 2 kilometer side. It can, in one point, in one gateway, if you have the gateway at one place, up to 2 kilometer length, it can catch the data from sensor.
Okay.
So now we are planning to extend this work. Actually, we are on job for real field implementation. Now, as of now, it is laboratory scale small test equipment we can think of.
Okay.
Not yet ready for field deployment, but I can tell for the people who are at educational institute, I have been benefited by this system to do many tests, because as I was telling, in laboratory we have problem of fund. We cannot buy many equipments, but using this technology, we are doing test of most of our laboratory test requirements are satisfied by this technology, by indirect measurement of so many parameters.
Okay. So, adding on to that, sir, regarding that shrinkage cracks,
Yes.
based on the operational limit, you have already developed a system for evaluating that.
Yeah.
I
We
think,
have also developed a system for that is also very useful. How to, when your structure is not properly cured,
yeah, right.
the stakeholder will get immediate information. So this program will give you an alert notification whenever you require, right? During the coding, you have to make a code and send alert notification at a particular appropriate time so that you can intervene to
Yeah. Sir, my idea was actually, so based on that message, why cannot we make a automatic curing, means watering system, something like that?
Yeah, that is another way. This is only for monitoring, but
Yeah.
what you are telling, automatic curing system, uh, we have
That
not worked on
basically,
that. That is a great idea.
major problem reported by clients, right? They, as a common man, when they see some minor cracks itself, they will be
Yeah.
upset.
Yes.
So, yeah, I think that can be extended to that side
Yeah,
also.
definitely. So that is another way of sorting out. So this is what I told. It is not solving the problem. It is kind of notifying you that
Yeah.
there is a
Yeah.
impending problem. How do you solve? Again, we have to think on that.
Okay, sir. Thank you.
Thank you very much.
Any more questions? Then, Vinod, shall we? If no more questions are there, we can wind up.
Dr. Pradip Sarkar, sir.
Yeah.
Hello, am I audible? Okay.
Yeah, I can hear you.
Okay. Hello, sir. We are glad to be a part of this session. It was a very substantive lecture and presented in a very eloquent manner. On behalf of the Civil Engineering Fraternity, I would like to thank you for your distinguished lecture. Once again, thank you so much, sir. I also thank all participants for being in this session and for really standing up for this course. Thank you, sir. Thank you very much to all.
Thank you very much.
Thank you, Pradeep.
Thank you, sir. Thank you.
Thank you for the nice presentation in the
Thank you,
simple
sir.
way. I think it's a new technology.
Yeah. And
Please
I have chosen this because most of my Malayali students have working in this project.
Oh, okay.
Thank you.
Any papers are published?
Yeah.
This,
what I have presented is already published in one AC journal.
Oh, yes, okay. AC journal.
One ASC, American Civil Engineers. Yes.
Okay.
On construction monitoring, construction management, they have a journal. In that journal.
Good. And you have a new topic.
Yes, sir.
I think chances are there to work.
Yeah. That's what anybody can start working with less cost of the project.
Good. Thanks once
Thank
more.
you. Thank
Okay,
you.
I will contact you.
Yeah, I will take a leave then.
Okay.
Thank you.